Good evening, everyone. Thank you for waiting. If you don't remember me from last time, I'm Dr. Jeff Rich. I'm an astronomer and the outreach lead at the Carnegie Observatories. John couldn't be here tonight, so I'd like to welcome you on his behalf to our third lecture in the series this spring. I'd also like to remind you that tickets for the next lecture will be available tomorrow morning at 10 a.m. Dr. Ethan Nadler will speak about the search for dark matter physics and how next-generation telescopes will help us understand that. So that lecture will be here in 2 weeks. I look forward to seeing you all back here. Again, I'd also like to take the opportunity to thank the Norris Foundation for their support, which makes the series possible, as well as all the staff here who help make these events a real success. It's my honor to introduce tonight's speaker, Dr. Abigail Polin. Dr. Polin carried out her graduate studies at UC Berkeley, creating new computer simulations of exploding white dwarfs in an effort to predict the signatures of a particular kind of supernova called a Type 1a, and to understand how they're made. After completing her PhD in 2020, Dr. Polin joined us here in Pasadena, jointly appointed as a Carnegie Fellow, as well as the Burke Fellow in Theoretical Astrophysics at Caltech. She's continued her research on supernova, as well as other transient events. She's been awarded millions of hours on cutting-edge supercomputers to create these simulations of supernova and exploding stars. During her time in Pasadena, she has also used telescopes at our Las Campanas Observatory to observe some of these transient events. And in 2021, Dr. Polin was recognized for her highly impactful work as the recipient of the National Energy Research Scientific Computing Center Early Career Award. Tonight, Dr. Polin is here to speak about one of my favorite topics in astronomy, how we measure distances. This is really relevant to us here in Pasadena, as Carnegie astronomers have played a key role in understanding the size and shape of our universe. So I'm looking forward to hearing what Dr. Polin has to say. Please join me in giving her a warm welcome.
Thank you. Hopefully this mic is on, yes. Thank you all for coming, and thank you to the Huntington for having us. I don't know how I can go after that music, but we're going to try. Again, my name is Abigail Polin. I am a postdoctoral researcher at Carnegie and Caltech. And I've been interested in space ever since I was a kid. I was lucky enough to grow up somewhere with clear skies that I could have the experience of seeing the Milky Way. And ever since, I've had questions. And my job is so cool because every day I get to ask those questions, and sometimes I even get to answer them. So typically I study supernovae from a theoretical perspective. So I do a lot of math, a lot of computer simulations to ask how a star explodes at the end of its life, and to ask what that would look like if we saw it. And I love this topic because, well, supernovae create everything we're made of, right? They create the calcium in our bones. Kilonovae create the gold in our wedding rings. And so understanding that is truly special. As Carl Sagan says, we're all made of stardust. Today, I'm going to talk about, though, one of the most important implications of the kind of work that I do. And that is because we use supernovae, a little bit of a spoiler here, as some of our cosmological distance measures. So let's talk about this. I've labeled the talk a century of distance measures because over the last 100 years, we've made bounds in this field, and a lot of that science has been done here in Pasadena. And so let's get started. So the fundamental question we're trying to answer today is, how can we tell how far away something is from us? And it seems like a simple question, right? And I know I spoiled a little bit of this playing with my pointer a minute ago, but does it still seem like an easy question if I show you this field of stars and ask you which one is the closest and which one is the furthest? We might be able to guess, right? We might have some inferences. Maybe we could say this one down here, the biggest one on the object is in the image here, is the closest, and maybe one of these little ones is the furthest. And that would be true if all stars were the same brightness, but they're not. And in fact, I, as an astronomer, would not be able to just look at this image and tell you the answer. I actually don't know which the closest is, but I do know which the furthest is. So if we take a look at these two in the center that look almost identical to us in this photometric image, you might be surprised that they're very, very different. So this one here is a star in our Milky Way. It's 25,000 light years from us. And tonight you'll hear me use both light years and parsecs as units of distance. So a light year is the amount of distance that light will travel in 1 year, right? And a parsec is basically 3 light years. So this star is in our Milky Way. The light emitted from it took 25,000 years to reach us, but that's still, in astronomy terms, fairly close. Its neighbor, though, is not a star. It's actually a quasar. And quasars are much brighter than stars. So it's 2 billion light years away from us. Yes. But it appears the same in this image if we just take one snapshot through our telescopes. So perhaps this doesn't seem like the easiest question anymore. How can we tell how far away something is from us? So tonight we're going to try to answer that and also try to motivate why we might care how far away something is. So let's go through an exercise. I want you all, this lovely background image, give me a thumbs up. You liking the talk so far? Yeah, thumbs up? But one at a time, look at the tip of your thumb, kind of lined up with this, and people watching at home, try to find a background with objects on it like this, maybe some pictures on your wall or something, not just a blank wall. And one after the other, close one eye, then the other eye. One eye, then the other eye. And I look silly doing this, and you look silly back, but you should notice, yeah, exactly, I heard it in the audience. Your thumb kind of jumps, right? It shifts back and forth. That in astronomy is what we call parallax. So if we have a star, and we think that it's way closer to us than these background objects in space, we can take one image up here in January and see that it lines up like this, and then wait 6 months, take another image, and see that star jump from side to side, right? And if you're good at math, if you know even just a little bit of basic trig, you can take the distance between us and the sun and use that to see how much you've shifted here. And again, assuming these are very far away, use it to calculate the distance to that star. And this is just like what we just did, but instead of 2 eyes, we're having the Earth here and then the Earth here. So the blinking of the Earth takes 6 months. But let's try this one more time. And this time I want you to first take your thumb and put it maybe 6 inches in front of your face and try. And then again, as far as you can reach out and see if you notice anything. So you should see exactly. When the thumb is closer to us, it looks like it's jumping much further, right? That's just part of the geometry. But when your thumb's further from you, it just jumps a little bit. So parallax is something we can only use for reasonably nearby objects. Once they get too far from us, the little side-to-side jitter is smaller than what we can resolve easily with a telescope, or even at all once we get far enough. So we can use parallax reliably, and it just involves math, to study the distance of objects up to 4 kiloparsecs from us. And 4 kiloparsecs is 4,000 parsecs, so 12,000 light years. And that, again, seems like a lot, but that still leaves us only within our Milky Way. So tonight, we're going to climb together what's called the cosmic distance ladder. And the concept here is that we need to start with what we can do for the closest objects, and then use those to calibrate our measurements to the next farthest objects, and the next farthest objects, and so on and so forth until we can get out into space and learn some facts about the universe. So the next rung of our ladder comes to us from a woman named Henrietta Leavitt. And Henrietta Leavitt was what's known as a Harvard computer. So this was the early 1900s, and at the time, most places would not employ women to be astronomers. But there were plenty of talented women who were really good at math and science who wanted to do science. And so Harvard, amongst other places, realized that they could hire these women for very low salaries, or in the case of Henrietta Leavitt, nothing. And these women did a lot of actual science. They did a lot of data collection and analysis for the astronomers that until more recent history was kind of overlooked. Not in this case, though, because Henrietta Leavitt, in addition to doing all the data analysis, made one of the biggest discoveries of the time. So Henrietta studied what is known as a Cepheid variable star. So a Cepheid variable is a star, and I'll explain the plot in a second. Over time, it gets brighter, and then dimmer, and then brighter again. And so what we're looking at here is kind of a graphical representation of that. So on the x-axis, we have time, and on the y-axis, we have brightness, measured in a unit called magnitude that we use a lot in astronomy, and you're going to see a lot tonight. So magnitude is a logarithmic unit, which means that the difference between 19 and 18 is a factor of 10 times brighter. And for historical reasons, very annoyingly, the smaller number is brighter. So you'll always see me plot this such that brighter is up and dimmer is down, even though the smaller numbers are on top. So Henrietta Leavitt was given this Cepheid variable, these photographic plates with Cepheid variable stars on them. And she was asked to make plots like this, basically, of measuring their brightness over time and recording that for the astronomers. And what she realized is that there's actually a relationship that if you measure the period between, or the time between brightest peaks, and compare that to the brightest point in the star's cycle, we fall on a line. And this is profoundly useful because the period of these Cepheid variables is very easy to measure. And if we know the period, we know how bright they're supposed to be. And so we can use that to tell how far away they are. So the same thing's true. This is what we call a standard candle, right? So the same thing's true for any source of light. If I have a light bulb, and I know it's a 60-watt light bulb, I know how many photons per second come off of that light bulb because I know it's a 60-watt light bulb. We call the truth of this object the absolute magnitude, right? So the truth about its brightness is the absolute magnitude. And so if I have a 60-watt light bulb, I know that that is brighter than a 30-watt light bulb. It's emitting more photons per second than the 30-watt light bulb. And I know how to compare their absolute magnitudes. But if I take my 60-watt light bulb and I move it far away from me, it will also appear dimmer. And that's what we actually get to measure when looking through a telescope, how bright it appears to us, right? It's the same concept of that field of stars. Just because it looks dimmer doesn't mean it intrinsically is. So, if we measure the apparent magnitude, so how bright it looks to us, and we know that it is a 60-watt light bulb, we can tell how far away it is. But in order to do that, we need to know the wattage of the light bulb. And that's why Cepheid variables are so important in this story. They were our first example where we got to know the wattage of the light bulb. And we could figure that out by just measuring their period, right? So coming back and making sure we knew the time between peaks. So the first application of using Cepheid variables as standard candles gave us a result that, once again, humans were surprised that we are not at the center of everything. In fact, this is an artist's representation of the Milky Way based on what we know of our data and what we think it looks like now. And we are not in the center. We're down here in one of the spiral arms. So the first thing that they did with Cepheid variables was measure the distance to the center of the Milky Way and find out it's quite far from us. Or, nearby, depending on who you're asking. But it's 26,000 light years, approximately, from the Milky Way. They can go further, and they use these Cepheid variables to map out the size of the Milky Way, the distance to our neighbors, just started to form a map that eventually gives us this kind of knowledge of our home galaxy, right? And these numbers were off at the beginning, but they were still remarkably close. So, this isn't what the Milky Way looks like to us, though, right? This is, right? If we're lucky, if we're incredibly lucky, this is what the Milky Way looks like to us. And sorry, it's a little pixelated here. But at the same time that we were using these Cepheid variables as standard candles to map out our Milky Way, there was a debate going on about the objects here. And this is something, I'll name it in a second, that you can see with binoculars most places, but with the naked eye, if you're very lucky, in a dark sky. And they're just kind of smudges on the sky. And at the time, we called them spiral nebulae. There's a couple. This is the nearest one, the biggest one. And astronomers were debating, are these spiral nebulae just gas formations in the Milky Way, or are they something else? And we now know there's something else. So at the same time we were doing all of this and we were having all these debates, right here in Pasadena, Gregory Hale was building the world's largest telescope. Again, he actually did this about 4 times, I think. He was the first in Pasadena here at Mount Wilson. He was the first to build a 40-inch telescope. He was the first to build a 60-inch telescope. He was the first to get to 100 inches, which is what we're seeing here. It's still operational, although not used for science anymore because the light pollution of LA has gotten too bad. But you can still go up to Mount Wilson, and they do some public nights and everything. I encourage you to check it out. It's very cool. And then later, he was also the first to a 200-inch telescope in Palomar. So at the time, we didn't get to look through an eyepiece down here. You had to sit up here in a cage and put glass plates in the telescope, and those glass plates work just like film. Hopefully, I'm not the only one in this audience old enough to have used film before, but you know, the light just exposes and you get an image on these glass plates just like photographic film. And here's a picture of someone you may have heard of, a Carnegie astronomer, little well-known, Edwin Hubble, doing exactly that on the 100-inch telescope. So he's looking through here and there will be a glass plate in here having images or spectra being exposed upon it. So this is Hubble on the 100-inch telescope, and he was very interested in these spiral nebulae. Both the question of what they were, what that implied, and what he was looking for were kind of flashes in these nebulae called novae, which we now know are kind of stars, the outer portions of stars burning away without exploding the whole star. And so 100 years ago, in 1923, he took an image of this spiral nebulae, the Andromeda galaxy, that changed astronomy forever. So this is what he saw. Not quite. This is what we know it looks like today. So if we rotate it, and we can put a plate on top of it, this is what he saw. And Hubble was up here doing this over and over and over again, and taking images of Andromeda so he could point out these novae as they appeared that weren't in the previous plate, or weren't in earlier plates. And this plate, taken October 6, 1923, you can see he marks a nova, he marks a nova, he marks a nova, and then he crosses that out and writes var. And it's actually really hard to see. At work, we have one that's actually blown up to about this size, and you can squint at it and see it, but there is a variable star in there, I promise. And it's a Cepheid variable. And so Edwin Hubble could use the period of the Cepheid variable to measure the distance to the Andromeda galaxy and prove beyond a shadow of a doubt that it is outside of the Milky Way. And we are not alone in the universe. There are other galaxies out there. And put an end to the debate of what these spiral nebulae are. They are galaxies. So just for fun, though, I decided to overlay, because I saw somebody else do it once and it was very cool. This is what this would look like if that Cepheid were in the Milky Way. So it is very easy to tell the difference. Light dies off as 1 over distance squared. So as we move further away, it gets very rapidly harder to see these things. So Andromeda is its own galaxy. Hubble didn't stop there. He decided to keep looking for these Cepheid variables in other spiral nebulae. And he eventually mapped out the distance to about 30 galaxies, the distance between us and them. And he noticed something peculiar. And that is that as we go further out in distance, and all these dots are the values for different galaxies, if we compare that to the velocity of the galaxy that we get through spectral information, as we get further away, these galaxies are moving away from us faster and faster, with the exception of these few down here, which are coming towards us, and Andromeda is one of them. Someday, Andromeda and the Milky Way will merge. So this is called the Hubble-Lamite law, and it's called the Hubble-Lamite law, and pardon my French there. I don't know if I'm saying that right. Somebody can tell me later. Because Hubble actually wasn't the first to notice this. A French astronomer, Lamite, published this 2 years before Hubble, but he only published it in French. And it took 4 years for it to be translated to English. And so Hubble got credit for it in the English-speaking world while we were still working on that translation, and now they share credit. But what does this mean, right? What does it mean that the further we go away from us, everything's running away faster, right? Are we that unpleasant? And what this tells us is that the universe is expanding. So this was going on at this dawn of general relativity. And at the time, we didn't have a solution that explained this, but it wasn't too long before Einstein came up with a solution to the universe, to general relativity, that it's possible to have a universe that is expanding. And what I mean by that is that the space in between things is growing. So this is a Hubble deep field image. And if we let this universe expand, it's something I can do fairly easily with a computer, right? So I can expand it 20%. And if I overlay this with the original, you can see that to this galaxy at the center, it looks like everything's moving away from it. And everything, as we go further and further out, it's moved away further and further. And so that's the perspective, right? That it looks like things, as the space expands, it looks like things are running away from us faster and faster. But this does not mean we're at the center of the universe, because every galaxy sees the same thing, right? If you're your reference point and space between me and you is growing, it's going to look like I'm running away from you. That's just how it works. So this also implies something cool, and that is if the universe is expanding and everything's spreading out, it means that once upon a time, everything shared the same space, right? And that's what we in astronomy call the Big Bang, right? And so you can take this plot Hubble made, the Hubble-Lamite law, and calculate the slope of this line and use that to ask when the Big Bang happened, right? So this slope is something we're going to focus on for the rest of the evening, and it's called the Hubble constant. And the original value here is somewhere around 500, and then the units are velocity divided by distance, so kilometers per second per megaparsec, right? And it's kind of the rate that this expansion is happening. And you can use this slope and invert it to ask when the Big Bang happened, how long ago. And if you do this with this original value, you get that the Big Bang happened about 2 billion years ago, which is wildly off. The Earth is about 4.5 billion years old, so that makes no sense. But we have better numbers now. But it's one of the reasons we care so much about what this number is. We need to understand Hubble's constant in order to understand our place in the universe, when the Big Bang happened, how long ago, etc. So we've been hunting for this number ever since, and a lot of that hunting has been done by Carnegie astronomers. So up here, this is actually, I think, Lamite's number, because it's a little over 500, or a little over 600. Highlight some Carnegie astronomers here. There's a big gain in the 1950s when we realized that there's not just one type of Cepheid star, there are two types of Cepheid stars, and we need to standardize them differently. And so that's the biggest drop you see. But another Carnegie astronomer continued this work in the 90s, and we're still working on this today. One more I should point out is Wendy Friedman. She was the PI of one of the main science goals of the Hubble Space Telescope, aptly named Hubble, was to measure Hubble's constant with this new technology. And ever since the 60s, we've kind of been oscillating between 50 and 100 kilometers per second per megaparsec. So it maybe wasn't terribly surprising that the HST gave us a number of 75, right in the middle, take the average. So this seems great. We're narrowing on a number, but all of this is done, again, in the reasonably local universe. So Cepheid stars are only so bright. And as we look at galaxies further and further away from us, you can kind of imagine it, if you think about that Hubble Deep Field, they look smaller and smaller. So their stars will appear closer and closer together. So not only are these stars dim and hard to see, but it's hard to pick them out from their neighbors, right? So there is a distance limit with which we can observe and measure a Cepheid variable, and that's around 40 megaparsecs. This time is 10 to the 6 million, so 40 million parsecs are 120 million light years. Seems far, but again, not maybe in the scale of the universe. So what we need now is a brighter candle. And that comes into my favorite topic, and that is supernovae. So, not me, I hope. So, type 1a supernovae are the explosion of a star we call a white dwarf. And the white dwarf is kind of a leftover core of a younger star, but it is so dense that it is supported by what's called electron degeneracy pressure. So what's fighting the gravity of this star, keeping it up, right, is the fact that when you get electrons close enough to each other, they don't want to occupy the same space. They kind of repel each other like a magnet. And there's a weight limit to which this electron degeneracy pressure can keep a star up. And we call that weight limit the Chandrasekhar mass limit, and it's about 1.4 times the mass of the sun. So if this white dwarf exists in a binary with another star, something cool can happen. So that star can donate mass to the white dwarf, and that white dwarf grows and grows and grows in mass until it hits that Chandrasekhar mass limit, at which point it explodes. Because it starts to collapse, and it gets all hot, and it triggers an ignition, and it doesn't have time to puff back up and cool off. So it gets what's called a thermonuclear runaway, and you just rapidly burn to the point of there's no way to turn it off. And we get my favorite type of supernova, a type 1a. All right, so here's what these look like when we observe them from Earth. So this is supernova 2011 Fe, which is one of my favorites because it's one of the closest, so we have some of the best data on it. It's 6.5 megaparsecs, so closer than our limit of our Cepheid variables. So we can use this, and hopefully some Cepheid variables here, and compare the measurements we get, right, to try to tell us what the wattage of this this 1A is, right? So it goes off. You can see it gets bright slowly, and then it gets dim slowly again. And we can measure that in what's called a light curve. And again, we have this pesky magnitude scale. This time I'm putting it in absolute magnitude because we know how far its host is. And time from peak here, so this is the 0 point in time, but it's just time in days. And supernovae, type 1a supernovae, their light curves look like this. There's an initial rise, there's a peak, and then it falls off and dies slowly. And that's because these are supported in their center by radioactive nickel. And nickel has a half-life. So basically, the nickel decays, and it will reach a peak, basically, compared to the time of its half-life. And that nickel decays into cobalt, which decays further, and that supports this tail here. So, another Carnegie astronomer comes into play, and that's Mark Phillips. And he realized something very cool about these type 1a supernovae. And that is if you take their light curve and take a measurement of their brightness at the time of peak, wait 15 days, and take another measurement of the brightness, you get a value called delta M15. Just delta is change, so change in magnitude after 15 days, right? And if we compare that to the brightest they get, yet again we get a line. We like lines, because lines, again, mean that if I measure delta M15, or kind of the width of the light curve, I can tell you how intrinsically bright the supernova is. So we have a brighter standard candle, right? This is a measurement easy to take, and it tells us what wattage our light bulb is. So we can use these to go up to, I think it's been done at least 600 megaparsecs with type 1a supernovae to measure distances. And that's far enough that we're getting past our local universe. We're getting into our historical universe a few billion years ago. And we can start to piece together the history of our universe and how we got here. And when this was done with type 1a supernovae, stretching out a few billion years ago, something remarkable was found. So initially we thought that maybe, the universe is expanding, but we thought logically all the matter in the universe should be pulling back on that expansion and slowing it down. And when we measured all the galaxies a few billion light years away, we saw the opposite. We saw that they were running away from us faster than what we would expect from the rate of expansion today. So not only is the universe expanding, but the rate of that expansion is accelerating. And this discovery was so mind-blowing. It was a very natural Nobel Prize. In 2011, the Nobel Prize was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees jointly for the discovery that the expansion of the universe is accelerating, and learning this from these type 1a supernovae. So I think this is the coolest thing that we can learn from just asking the simple question, how far away is something, right? It's kind of mind-blowing that how far away is that can lead to our universe is undergoing an acceleration of its expansion. Pretty cool. So when you do this, again, you can get out to about 600 megaparsecs with type 1a supernovae, and we think we can go further. We just have to, right? We haven't done it yet, but there's no reason that that's the limit. We get a measurement of the rate of expansion today, h0, between 70 to 74 kilometers per second per megaparsec. So again, I told you the previous one was 75. This seems fine, right? We're all kind of settling in on a number. However, in 2018, a wrench was thrown into our plans. Yes, by Planck. So what I'm showing here is something called the cosmic microwave background. And it is kind of the limit of how far back we can look in the universe. Because before that, this is what we call the limit of optically thick. So before that, photons are so hot that they're bouncing off each other. They can't escape. They can't get to us. They can't even leave to try to get to us. So this is as far back as we can look. And what you're looking at here in red and blue are kind of temperature fluctuations at this limit. So red is hot and blue is cold. And it looks random, but it's not. We can do a bunch of math to this, take a power spectrum, and get something that looks like this. And it's possible to use these as, instead of a standard candle, a standard ruler. So if we measure this analysis, kind of the characteristic size of these perturbations, right? We can compare that number that it appears to be to the number we expect it to be. And that tells us what universe we're in. And one of the things that tells us is h0. It comes out of this measurement. So it's indirect. It's not as easy as just measuring a distance to this, right? But it gives us a Hubble constant of 67.6, which is statistically significantly different enough from the type 1a supernovae measurements to be a problem. This is what we call the Hubble tension. So there's a conflict here between these measurements made by type 1a supernovae and calibrated with our Cepheid variables, the Cepheid variables in the Milky Way, and the measurements made with the cosmic microwave background. And we've come up with other ways of calibrating these type 1a supernovae, various ways, the tip of the red giant branch, surface brightness fluctuations, which are newer and less historic, so I'm not going to go into them today. But suffice it to say, every way we can come up with so far of calibrating these supernovae still gives us an answer that's different from the early universe answers. And so this could mean one of two things. It could mean there's some physics we don't understand about how our universe exists and what type of universe we're in. Or, in my opinion, more likely, because it's a simpler solution, there's something we don't understand in these measurements, right? We could be looking at another situation like the 1940s where there's two types of Cepheid stars, right? And this is what I study, right? So if this is that Phillips relation we talked about earlier, this is, again, the width of the light curve, the change in magnitude over the first 15 days after peak, and the brightest they get, and this is that Phillips relationship. And most type 1a supernovae do lie on this relationship, but we've observed a lot more supernovae since 1993, a lot. And it turns out there is a very wide variety of type 1a supernovae. We have bright ones, we have dim ones, we have fast ones, we have slow ones, one fish, two fish, red fish, blue fish, right? And so now the problem for scientists like me is asking the question, why do we see so many different types of type 1a supernovae? And the answer is because there's more than one way to explode a white dwarf. But more complicatedly, how do we know which ones we should use as our standard candles? And how do we standardize the other ones? So this is active current science that anyone in my field would give you a different answer to. We don't know the answer to this yet, but this is part of the hope for the future. There's another hope for the future of this tension, and that comes from a totally different measurement that is unrelated to the supernovae or the CMB. So a third independent measurement can be made that hopefully will give us an answer. And that is through gravitational waves. So some of you may have heard of LIGO. It is the world's first gravitational wave interferometer, so a gravitational wave observatory. And this is me. I have a special place in my heart for LIGO and gravitational waves because this is where I got started as an undergraduate intern. In 2012, we were here installing the new interferometer Advanced LIGO, which is the one working today. So how LIGO works is, well, let's take a step back, actually. What's a gravitational wave, right? So it turns out anytime a non-spherically symmetric mass moves, any non-spherical symmetric, I'm not spherically symmetric, you're not spherically symmetric, every time we move in a non-spherically symmetric way, we actually emit ripples in the space-time around us. And now for us, those ripples in space-time are very, very tiny, like insignificant. However, if you take something incredibly massive, like say a black hole, and you give it a binary companion of say another black hole, and you let them orbit around each other, they're emitting very, very strong gravitational waves. And those gravitational waves distort space-time, so they change the distance in between things, right? So LIGO is designed such that it can measure those distortions in space-time, specifically from binary black holes and binary neutron stars. So these black holes, they're spinning around each other, they're getting closer and closer and closer, they're gonna merge. They emit really strong gravitational waves that go through Earth. And how it works is that LIGO has 2 arms, and we shoot a laser down each arm. And when a gravitational wave goes by, it distorts space-time such that one arm grows and the other shrinks, opposite each other. So what we're attempting to do is measure the difference between if we shoot that laser out, when it comes back versus when we expect it to come back. And we can do that pretty easily by letting them interfere with each other, right? So we can measure the difference not just from one arm, but 2, because this one's growing and this one's shrinking, and we're emitting lasers at the same time. So if nothing happens, they should come back at the same time. And if a gravitational wave goes by, they should come back at different times. And this is only possible with a giant structure like this. So each of these arms is 4 kilometers long. It's a really powerful laser, which requires a really, really large vacuum system. And actually, these lasers bounce back and forth several times before we take this measurement. And even then, we like to say we're trying to measure a distance that's the equivalent of if you take a Great Lake and add 1 more drop of water to it, the amount that the surface level rises. So in 2012, this felt like science fiction, really expensive science fiction. But it works. It does work. This was another recent Nobel Prize when this worked. For the first time, we detected a binary black hole merger by detecting the gravitational waves. And when we detect these gravitational waves, part of the information we get is a really, really precise measurement of how far away the source of these gravitational waves is. So I don't need to do any trigonometry. I don't need to calibrate it on any Cepheid stars or the tip of the red giant branch or anything like that. I just know how far away it is, right? And unfortunately, for a binary black hole, which is the most common LIGO source, that's not all that useful. I mean, it's really useful for other science, sorry. It's not all that useful as a distance measure because they don't emit any light, right? They're black holes. However, there's another source that LIGO can detect, and that is 2 neutron stars that are orbiting around each other and merge. And when that happens, they do spit out material, and that does create light. Light. And that, sorry. And that is what we call a kilonova. So here's a rendition of what this looks like. So these are the 2 neutron stars orbiting around each other, and you can see the distortion of space-time, these gravitational waves, the artist's interpretation. They get faster and faster and faster, and then they merge, and when they merge, they spit out this gas. And this is actually one of the main sources of what we call our process elements, the very heavy radioactive material, not radioactive, sorry, the very heavy elements like gold and platinum are created in this kind of explosion, right? And so if it emits light, we can look for that light. And if we look for that light, we can see what galaxy that kilonova exists in, and we can use the gravitational wave information to tell us how far that galaxy is, and it's a totally independent distance measure. So kilonovae are what we call standard sirens, because we get the distance from the waveform. And we've seen exactly one of these. So the kilonova is GW 170817 is what we call the gravitational wave signal. And it's also called AT, so astrophysical transient, 2017 GFO, because we start with A, and then we go B, and then we get AAA, ABC, GFO. We get a lot of transients at this point. And this is what the data looks like for LIGO. And it's clearest in the LIGO Livingston. So there's one in Louisiana, there's one in Washington, and Virgo is in Italy. But you can see it most clearly. This, you can think of the ringing up of this frequency here is them getting closer, closer together, and then merging. And so there's a correlated signal in our Livingston Observatory and in our Hanford Observatory, and you can't see it in the Virgo data. And that actually gave us enough information that even though we know the distance to this, with just one of these, we don't know what direction, though. We just know how far. It could be in any direction. With the information combined by all three, we can give an approximate direction in the sky that we should go look for it. And another tie to Carnegie science, a little more dubious this time, is that when we finally found the optical signal, it was one of our telescopes that found it. And I include this because I was lucky enough to be there a month ago and take this photo. But this is the Henrietta Swope 1-meter telescope at our Las Campanas Observatory, which is where Carnegie science moved once the light pollution from LA got too strong to use Mount Wilson. And this is what it looks like in the optical. It's just this little dot here that we learn so much from. And again, 1708-17 just means 17th August 2017. So we've gotten exactly one of these, which is not enough to give us a meaningful measurement yet. However, LIGO is going to turn on again this month. And we're all waiting with bated breath to see if we get another one of these. And we all hope so, even though for people like me, it will mean not sleeping for 3 weeks. So, this is a nice compilation of a more scientific version from this nice thesis here of all of the different ways we measure H0. And I'm sorry the red doesn't show up very well here, but it shows that the measurements from the CMB, even the most sophisticated measurements to date, do not line up with our standard candles. So hopefully, someday, as we're working to understand our systematics, we will also get this third independent measurement from gravitational waves, which, in my opinion, will be what's actually needed to put this tension to rest. So, just before we end, let me remind you of what we talked about today. How can we tell how far away something is? Well, we can climb our distance ladder. For nearby things, we can use parallax. We can build upon that with Cepheid variables. And finally, we can look at our supernovae to tell us how far away the historical universe is. And we learn so much from this. We learn the history of our universe. We learn that the universe is 14 billion years old. We learn that we're an expanding universe and that rate of that expansion is accelerating. We also have more questions. We have this Hubble tension of why don't these numbers from our direct measurements of distances match with what we infer from the early universe. And we're still working on understanding whether or not this indicates more physics or if there's just something we don't understand in our existing measurements. So thank you again so much for coming today, and I would really love to take your questions.
Thank you so much. If you have any questions, we have microphones at the top of the aisle, so please head to the microphone so folks on the live stream can hear you. While you do that, we actually had some questions from the live stream, so I've got one for you already.
Great.
Someone, let's see, Joan asked, do you think we will eventually reclassify what we currently call type 1a supernova into subtypes that better describe their differences?
I think I know who asked that question. Thank you for it. Yes, and we already do. We annoyingly tend to name them after the first one discovered of the kind. So we name them 91BG-like supernovae, or 99BY-like supernovae, or 91Ts. But people like me are trying to kind of reconfigure that to put physics behind those classifications. So instead of a 99BY, we can say a subchandrasekhar mass explosion. Or instead of a 91T, we can say a superchandrasekhar mass explosion. To try to recategorize instead of just noticing that they're different, understand why they're different. And that's the bread and butter of what I do every day.
Very cool. So why don't we start on this side?
Okay, I actually have two questions. One's really quick, though. How many kilonova do we expect to potentially see in a year or a decade? Do we have a theoretical idea of that?
Yes and no. It's highly debated. So the first one we saw was immediately after we turned LIGO on for that run. And so we were all really excited. We said, maybe the rates of these are much greater than we think they are. And it turns out we've now had LIGO on a lot longer since then, and we haven't seen any more. So best estimates are maybe 1 a year, I think is likely, but there are pessimists that say we'll never see one again, and optimists that say we're going to see 40. So.
And the second question is that I know that spectroscopic parallax was really useful in calibrating the Cepheids. Now that direct parallax has been taken out so far, 12,000 light years, is there still a place in modern astronomy for spectroscopic parallax? Is it still used to measure distances?
You know, I'm not sure. Spectra tell us a lot of other important things, but I'm not sure that there's anywhere we still use spectroscopic parallax, but maybe one of my colleagues will come yell at me afterwards.
Thank you.
You switch to that side?
Yes. Can you go back to it was near the beginning of the screens about, that showed a picture of the Milky Way.
Yeah.
And what I'm wondering is yes. So you showed where we are on that,
yes.
Now, when you look up, whichever way it would be angled,
Yeah.
how do you see through the big, all the stars in the middle to know, like that little section of white up at the very top? How do you know that's there? Because how do we see that?
With great difficulty. So it comes down to the fact that, yes, it's much harder to look through this,
Yes.
right? It's dusty, there's a lot of stuff there. But we can rely on the fact that different wavelengths of light travel more or less easily through things like dust, right? So this is a composite knowledge made from, say, if we look at one wavelength, we'll be completely blocked here. But if we look at another wavelength, some of this stuff becomes transparent for us.
Interesting. Okay, thanks.
So I got another question from online. Which new telescopes, JWST and any telescopes that are planned, will help get better answers in measuring distances?
Hopefully all of them. JWST is very exciting because a lot of our uncertainty, especially in type 1a supernovae, now comes from the fact that we don't understand them in the infrared very well. So that's if we go beyond red light, what we measure as heat, if you've ever seen an infrared camera. And that's what JWST is. It's an infrared telescope that has the capability of looking farther in the infrared than we've ever seen before. So we're going to get a lot more information about infrared supernovae, and we're going to see them further than we've ever been able to see them before. But ideally, all of these. So JWST is going to be helpful. LSST, the survey done on the Vera Rubin telescope, is going to see orders of magnitude more supernovae than we've ever seen before, so much that we're all arguing about how we can even deal with that much data. So it's a very exciting time for us transient astronomers.
Back to this side.
Yeah, how does redshift figure into these measurements?
Yes. So redshift can mean a couple different things. So it's another proxy for distance, typically. But it's also the Doppler shift, so it's more tied to the velocity aspect of it, right? And so how we know all of these velocities is because we took a spectrum of those objects, and we look at an atomic line that we know where it should appear if that object were at rest, and that shifted due to the Doppler shift. And so that's how we measure the velocity. And that's more of the proxy for redshift, is the velocity half of things.
So do we use that to determine how quickly things are moving away from us?
Yes, exactly.
Okay, thank you.
Got another question on this side?
Yeah, three questions about the effect on the accuracy of the measurement.
Yes.
What about dust,
Yeah.
distortion of space,
Yes.
and black matter?
Yeah. So It's a lot harder a problem than I make it sound. And one of the things you mentioned, dust, is kind of our biggest enemy. Because if there's dust in between a supernova and us, it makes it look redder, and it makes it look dimmer. And so if we're not accounting for that dust properly, then we're underestimating the brightness of that supernova, and we're calibrating its distance wrong. So a lot of the science we do, and especially the supernova cosmologists, is looking for ways that we can tell exactly how much dust is extincting that supernova, how much is in between us, by looking at things like their local environment and the colors of the supernova. So it's kind of one of our biggest problems. You are totally right.
So my question is, the Gravity Wave Observatory, it seems like it's one of those things that we would like on all the time, because it's like when an event happens, we kind of go, we got to look around quick to figure out where this is happening. But I don't think it's practical, and you said it's turning on. Is it extremely expensive to run? What would be?
So, ideally it would be on all the time. However, the way we kind of operate it is less about the expense of keeping it on and more about the fact that we want to make improvements, and it has to be off when we're making those improvements. So we have engineering runs in between observing runs, where we take it and we say we want to see if we can improve our sensitivity in this way by upgrading this part of it, and it has to be off when we do that. So,
thank you.
Yeah.
Another person on this side?
Yeah.
So LIGO is looking at these gravitational waves.
Yes.
Isn't there a lot of gravitational waves, or is there only one?
There are, and that's why we're looking for the black holes, right? They're the strongest source of waves. So we're looking for the waves above kind of what we call the stochastic background of gravitational waves.
So you have to filter all your noise out in order to take a look at these peaks of that.
Yep, and that's why we need such strong events like these mergers, that their signals are so much brighter than the noise.
And you're assuming that you only have one event at the same time.
Yeah, I don't know what would happen if we had two black holes go off at once, but I'm sure they've modeled that.
Just wondering.
But I'm sure they've modeled that into their data. But I don't know how many could go off at the same time before we couldn't get anything out of it.
So you said that the expansion of the universe is accelerating.
Yes.
But then doesn't that mean that maybe Hubble's constant isn't constant after all? And then this is simplistic thinking, but I guess what's wrong with it? And then if that's the case, then maybe the further back you go, the slower it was accelerating. So then that's why the cosmic microwave background number is smaller than the other ones.
Yes. So I should clarify very clearly. When I say h0 and the measurements of the h0 from the CMB, what I mean is the rate of expansion today. So for both of these, so for the supernovae, we're measuring the rate of expansion today, and we're inferring from the universe we think exists from the CMB what the rate of expansion is today. So they're comparing both numbers to each other, and there's a conflict. Yeah.
I see, okay. The complicated.
Yes, but yes, so the Hubble constant is explicitly the rate of expansion today.
Over here.
It was a very nice talk. Can you why is it that these gravitational waves give you an intrinsic distance measurement? What is it about them that you can get that intrinsically from them?
Oh boy.
Or is that complicated?
You know what? I don't know exactly how to answer that. It has something to do with the strain, the specific strain and the specific strength of the signal, but I don't know how to give you a more detailed answer than that.
Okay.
Yeah.
That's great questions.
Yeah.
Yeah, I hope I'm not asking a question that's already been asked, but what is it about the Planck measurement that gave you the CMB granularity data that even lets you make a statement one way or the other about the Hubble constant? What's that link?
Yeah, so basically when we look at the granularity in the CMB, what we're measuring is what is the dominant size of those grains. So when we take a power spectrum, so it tells us what the most common size of that is. And that size allows us to ask what universe would make that. And one of the parameters that comes out of that deterministic size is h naught today. It's one of the constants that pops out of the equation. So it's not a direct measurement. It's just, this is what h naught would need to be for those grain sizes to be that size.
This stuff is tough, right?
Yeah, it's very tough. And it's also, some of it is, coursework for me rather than what I do every day. So hopefully I'm getting it right.
Let's thank Dr. Polin again. We'll see you all back here in a couple of weeks.